Types of chemical reactions. Welcome to today's chemistry lesson. Every chemical change in the universe, from the rust on a nail to the fire in a furnace, follows one of just 5 fundamental patterns: decomposition, single replacement, double replacement, and combustion. Pay close attention. By the end, you will recognize these reactions everywhere in nature. Every chemical reaction can be sorted into one of 5 categories. In a synthesis reaction, 2 or more reactants combine to form a single, more complex product. In a decomposition reaction, one reactant breaks down into 2 or more simpler products. In a single replacement reaction, an element swaps places with another element in a compound. In a double replacement reaction, 2 compounds exchange their partners to form 2 new compounds. And in a combustion reaction, a substance reacts rapidly with oxygen, releasing heat and light. These 5 patterns account for nearly every reaction you will encounter in general chemistry. Synthesis reactions, also called combination or addition reactions, are the simplest of the 5 types. 2 or more reactants join together to form a single new product. The general pattern is A plus B yields AB. This can be 2 elements combining, an element combining with a compound, or 2 compounds joining together. A classic example is iron reacting with sulfur to form iron sulfide. Atoms in the reactants are rearranged and bonded together to create the product, releasing or absorbing energy along the way. Synthesis is the building reaction. It builds something more complex from simpler pieces. Look at the iron nail rusting on the slide. This is a familiar synthesis reaction you have seen 1,000 times. Iron metal reacts with oxygen from the air, and in the presence of water, forms iron oxide, the reddish-brown compound we call rust. The balanced equation is 4Fe plus 3O2 yields 2Fe2O3. Notice how 2 simpler substances, iron and oxygen, combine to make a more complex compound. Rusting is slow, but it is the same kind of combination reaction as burning magnesium and oxygen to make magnesium oxide, where the product is a new ionic compound. Synthesis reactions are all around us. They form water from hydrogen and oxygen, salt from sodium and chlorine, and even the proteins in your body from amino acids. The general formula for a synthesis reaction is A plus B yields AB. Here, A and B can be elements or compounds, but together they form a single, more complex product. Common examples include 2 hydrogen molecules plus 1 oxygen molecule yielding 2 water molecules. Notice that the diatomic elements on the left, hydrogen and oxygen, combine to form the compound water. In every synthesis reaction, the number of distinct products on the right side of the equation is exactly 1, no matter how many reactants you start with on the left. Decomposition reactions are the opposite of synthesis. A single compound breaks down into 2 or more simpler substances, which can be elements or smaller compounds. The general pattern is AB yields A plus B. Most decomposition reactions require an energy input, such as heat, light, or electricity, to break the chemical bonds holding the compound together. Heating calcium carbonate, for example, decomposes it into calcium oxide and carbon dioxide gas. Electrolysis of water splits it back into hydrogen and oxygen gas, exactly the reverse of the synthesis that formed it. Decomposition is the taking apart reaction. It breaks something complex back into simpler pieces. The image shows the electrolysis of water, a textbook decomposition reaction. An electric current passes through water containing a small amount of electrolyte, and the water molecule splits into its 2 elements. The balanced equation is 2H2O liquid yields, with electrical energy, 2H2 gas plus O2 gas. Notice the energy term written above the arrow, indicating that electricity drives the reaction. Twice as much hydrogen gas is produced as oxygen, exactly matching the 2-to-1 ratio in the water molecule. Decomposition reactions power many industrial processes, from extracting aluminum from its ore to producing quicklime for cement, and they are at the heart of recycling chemical feedstocks back into their pure elements. The general formula for a decomposition reaction is AB yields A plus B, the exact reverse of synthesis. Energy in the form of heat, light, or electricity is usually written above the arrow to show that it must be supplied. Common examples include mercury 2 oxide, when heated, yielding mercury plus oxygen gas, and calcium carbonate, when heated, yielding calcium oxide plus carbon dioxide. Notice how each of these starts with a single reactant on the left and produces two products on the right. Decomposition is the opposite direction of synthesis. If A plus B gives AB, then AB can also break back into A and B when energy is added. In a single replacement reaction, also called single displacement, one element replaces another element in a compound. The general pattern is A plus BC yields AC plus B. A pure element, A, swaps places with one of the elements in the compound, BC, kicking that element out and forming a new compound, AC. The key question is whether the reaction will actually occur, and the answer is given by the activity series. A more reactive element will replace a less reactive one from its compound, but not the other way around. For example, zinc is more active than copper, so zinc metal placed in a copper sulfate solution will replace the copper, producing zinc sulfate and depositing shiny copper metal on the zinc surface. Look at the image of iron nails placed in a blue copper sulfate solution. Within minutes, you can see a reddish copper deposit forming on the iron surface, and the blue color of the solution fades as copper ions are removed. The balanced equation is Fe plus CuSO4 yields FeSO4 plus Cu. Iron is higher in the activity series than copper, so iron atoms give up their place to copper ions in solution. This reaction is a vivid demonstration of single replacement, and it has been used for centuries in metal purification and recycling. The reverse reaction, copper replacing iron, does not occur. That is the rule of the activity series, the master key to predicting single replacement outcomes. The general formula for a single replacement reaction is A plus BC yields AC plus B. Element A replaces element B in the compound BC, forming a new compound AC and releasing the free element B. Examples include zinc plus hydrochloric acid, yielding zinc chloride plus hydrogen gas, and aluminum plus copper. 2-chloride yielding aluminum chloride plus copper metal. Whether the reaction occurs depends on relative reactivity. Use the activity series to check that A is more reactive than B before predicting a successful replacement. Always balance the equation after writing it, making sure the same number of atoms of each element appears on both sides. Double replacement reactions, also called double displacement or metathesis reactions, occur between two ionic compounds in solution. The positive and negative ions of the two reactants swap partners, producing two new compounds. The general pattern is AB plus CD yields AD plus CB. For the reaction to actually go to completion, one of three things must happen. A precipitate forms, an insoluble solid that drops out of solution, a gas is released and bubbles away, or water is produced from a neutralization between an acid and a base. If none of these happens, the reaction is just a mixing of ions and no net chemical change occurs. Double replacement is the partner swapping reaction. It dominates aqueous chemistry, water treatment, and acid-base neutralization. The image shows a classic double replacement reaction producing lead iodide, a brilliant yellow precipitate. When potassium iodide is mixed with lead-2 nitrate, the cations and anions exchange partners. The balanced equation is Pb2 plus 2, NO3 minus plus 2K plus 2, I minus yields PbI2 solid plus 2K plus 2, NO3 minus. Lead iodide is insoluble in water, so it forms a vivid yellow solid that drops out of solution. This is one of the most beautiful reactions in chemistry, often called the golden shower experiment, and it perfectly demonstrates how double replacement uses solubility rules to drive a reaction to completion. The general formula for a double replacement reaction is AB plus CD yields AD plus CB. The two compounds exchange their ions, with the cation from the first compound pairing with the anion from the second, and vice versa. Common examples include silver nitrate plus sodium chloride, yielding silver chloride precipitate plus sodium nitrate, and hydrochloric acid plus sodium hydroxide, yielding sodium chloride plus water. The hydrochloric acid plus sodium hydroxide reaction is a neutralization, where an acid and a base combine to form a salt and water. To predict whether a double replacement will occur, check the solubility rules. If a product is insoluble, it will precipitate, and the reaction goes forward. Combustion reactions are the fiery, energetic members of the reaction family. A combustion reaction occurs when a substance reacts rapidly with oxygen, releasing energy as heat and light. The general pattern is a hydrocarbon or other fuel plus oxygen yields carbon dioxide plus water plus energy. When there is plenty of oxygen, the combustion is complete, and the products are carbon dioxide and water. When oxygen is limited, the combustion is incomplete, and you get carbon monoxide, soot, or even unburned carbon plus water. Carbon monoxide is a toxic, odorless gas, which is why well-ventilated combustion is so important for safety. Combustion powers our cars, heats our homes, and runs the engines that drive modern civilization. The image shows a Bunsen burner flame, the iconic symbol of combustion in the chemistry lab. Methane gas flows up the barrel and mixes with oxygen from the air. When ignited, the balanced equation is CH4 plus 2O2 yields CO2 plus 2H2O plus energy. This is a complete combustion. There is plenty of oxygen, so the products are only carbon dioxide and water vapor. The blue cone in the center of the flame is where combustion is most efficient, while the outer envelope has a lower temperature. Propane combustion in a gas grill follows the same pattern. C3H8 plus 5O2 yields 3CO2 plus 4H2O, releasing about 2,000 kilojoules per mole of propane to cook your food. The general formula for complete combustion of a hydrocarbon is CXHY plus O2 yields CO2 plus H2O. For every carbon atom in the fuel, you need 2 oxygens to make CO2, and for every 4 hydrogens, you need 1 oxygen to make 2 H2O. For methane, CH4 plus 2O2 yields CO2 plus 2 H2O. For propane, C3H8 plus 5O2 yields 3CO2 plus 4H2O. For octane, 2C8H18 plus 25O2 yields 16CO2 plus 18H2O. Incomplete combustion produces CO, carbon, and other side products when oxygen is limited. Balancing combustion equations is a good test of your stoichiometry skills. Every chemical equation must be balanced to obey the law of conservation of mass. Balancing means adjusting coefficients, the numbers in front of each formula, so that the number of atoms of each element is the same on both sides of the arrow. A simple method is trial and adjustment. Start with the most complex molecule, balance one element at a time, save hydrogen and oxygen for last, and recount everything when you finish. For combustion reactions, a shortcut is to balance carbon first, then hydrogen, and finally balance oxygen last because it appears in multiple products. Never change subscripts inside a chemical formula to balance an equation. That would change the substance itself. Only coefficients can be adjusted. Mastering balancing is the gateway to all stoichiometry, the math of chemical quantities. Quiz time. Question 1. Which of the following is a synthesis reaction? Option A. 2H2O yields 2H2 plus O2. Option B. Zn plus QSO4 yields ZnSO4 plus Ke. Option C. 2H2 plus O2 yields 2H2O. Option D. AgNO3 plus NaCl yields AgCl plus NaNO3. Take a moment to think. The answer will appear on the slide in 60 seconds. Quiz question 2. The reaction 2KClO3, when heated, yields 2KCl plus 3O2 is an example of which type? Option A, synthesis. Option B, decomposition. Option C, single replacement. Option D, combustion. Take a moment to decide. The correct answer will appear in 60 seconds. Quiz question 3. A copper wire placed in a silver nitrate solution gradually becomes coated with shiny silver crystals. What type of reaction is this? Option A, synthesis. Option B, decomposition. Option C, single replacement. Option D, double replacement. Take a moment to think. The answer will appear in 60 seconds. Quiz question 4. Mixing sodium chloride solution with silver nitrate solution produces a white precipitate of silver chloride. Which type of reaction is this? Option A, synthesis. Option B, decomposition. Option C, single replacement. Option D, double replacement. Take a moment to decide. The correct answer will appear in 60 seconds. Quiz question 5. The burning of propane in a gas grill follows the equation C3H8 plus 5O2 yields 3CO2 plus 4H2O plus energy. Which type of reaction is this? Option A, synthesis. Option B, decomposition. Option C, single replacement. Option D, combustion. Take a moment to think. The answer will appear in 60 seconds. Solved problem 1, balancing a synthesis reaction. Aluminum metal reacts with oxygen gas to form aluminum oxide. Write and balance the equation. Step 1. Write the unbalanced skeleton equation using correct formulas. Aluminum is Al, oxygen is O2, and aluminum oxide is Al2O3. Step 2. Balance aluminum by placing a 2 in front of Al. Now we have 2 Al atoms on the left. Step 3. Balance oxygen by placing a 3 halves in front of O2. That gives 3 O atoms on each side. Step 4. Multiply everything by 2 to clear the fraction. The final balanced equation is 4Al plus 3O2 yields 2Al2O3. Step 5. Verify. 4 Al atoms, 6 O atoms on each side. The balanced equation is 4Al plus 3O2 yields 2Al2O3. Solved problem 2, balancing a decomposition reaction. Hydrogen peroxide, H2O2, decomposes into water and oxygen gas. Write and balance the equation. Step 1. Write the skeleton. H2O2 yields H2O plus O2. Step 2. Count atoms on each side. Left, 2H, 2O. Right, 2H, 3O. Step 3. Oxygen is unbalanced by 1. Place a 2 in front of H2O2 to get 4O on the left. Step 4. Rebalance hydrogen. With 2H2O2, we have 4H on the left, so put a 2 in front of H2O. Step 5. Check oxygen. Left, 4O, right, 2 in H2O plus 2 in O2 equals 4O. The balanced equation is 2H2O2 yields 2H2O plus O2. Solved problem 3, single replacement with the activity series. Will magnesium metal react with copper 2-chloride solution? Use the activity series to predict. Step 1. Identify the activity series positions. Magnesium sits high in the series, copper sits below it. Step 2. Write the potential reaction. Mg plus CuCl2 yields MgCl2 plus Cu. Step 3. Apply the activity rule. A more active metal displaces a less active one. Since magnesium is more active than copper, the reaction proceeds. Step 4. Balance the equation. 1 Mg and 1 Cu on each side, with 2 Cl on each side. Step 5. The balanced equation is Mg plus CuCl, 2 yields MgCl2 plus C. The answer is yes. Magnesium replaces copper, the solution loses its blue color and reddish copper metal deposits on the magnesium ribbon. Solved problem 4, predicting a double replacement precipitation. Will a precipitate form when solutions of barium chloride and sodium sulfate are mixed? Step 1. Identify the ions. Ba2 plus, Cl minus, Na plus, SO4 2 minus. Step 2. Write the potential products by swapping partners. BaSO4 and NaCl. Step 3. Check solubility rules. Sodium chloride is soluble in water, so it stays dissolved. Barium sulfate is insoluble. It forms a white precipitate. Step 4. Write the balanced molecular equation. BaCl2 plus Na2SO4 yields BaSO4 solid plus 2 NaCl. Step 5. Write the net ionic equation. Ba2 plus plus SO4 2 minus yields BaSO4 solid. The answer is yes. A white precipitate of barium sulfate forms, which is the basis of the clinical test for sulfate ions. Solved problem 5, balancing a combustion reaction with stoichiometry. Butane, C4H10, burns in excess oxygen. Balance the equation and find how many moles of CO2 are produced from 2 moles of butane. Step 1. Write the skeleton equation. C4H10 plus O2 yields CO2 plus H2O. Step 2. Balance carbon. Place a 4 in front of CO2. Step 3. Balance hydrogen. Place a 5 in front of H2O. Step 4. Count oxygen on the right. 4 times 2 plus 5 times 1 equals 13 O atoms. Step 5. Balance oxygen with O2. Place 13 halves in front of O2. Step 6. Multiply everything by 2 to clear the fraction. The balanced equation is 2C4H10 plus 13O2 yields 8CO2 plus 10H2O. Step 7. Apply the stoichiometric ratio. 2 moles of butane produce 8 moles of CO2, a 4-to-1 ratio. So 2 moles of butane yield 8 moles of carbon dioxide. Let us bring everything together. 5 types of chemical reactions organize the entire landscape of chemistry. Synthesis. A plus B yields AB, builds compounds from simpler substances, like iron plus sulfur, giving iron sulfide. Decomposition. AB yields A plus B, breaks a compound apart, like water splitting into hydrogen and oxygen. Single replacement. A plus BC yields AC plus B, swaps one element for another, governed by the activity series. Double replacement. AB plus CD yields AD plus CB, exchanges partners between 2 compounds driven by precipitation, gas formation, or water. Combustion. Fuel plus oxygen yields CO2 plus H2O, releases energy from rapid oxidation. The law of conservation of mass governs all 5. Every balanced equation has the same number of atoms of each element on both sides. Memorize the patterns, master balancing, and you unlock the language of chemistry. Excellent work today!